All right, I had a little gremlin in the studio here. It just kept playing another video over the top of this, and I couldn't figure out how to stop it from playing another video while I'm in the midst here. Hold on there. Okay, good. All right, so today we get to talk about dynamic programming. This is going to be exciting. I hope you're all excited. Dynamic programming is always a fan favorite, at least a staff favorite. It's a really cool technique that can speed things up quite a bit. However, it is kind of complicated, and you might have to learn it more than once. And that is definitely my experience. I feel like every time I have to do some DP, if I haven't done DP in a while, I have to relearn it a bit myself. So be aware that dynamic programming is not straightforward, and it will be cool, however. All right, on our cover slide here, we've got a picture of Richard Bellman. This is the computer scientist that came up with dynamic programming. And he was a brilliant computer scientist, hundreds of publications, including some 100 or so papers that were written after he had recovered from brain tumor. The guy is amazing. Leads us to, why is it called dynamic programming? The programming in dynamic programming is not computer programming, it's scheduling. So you think of like television programming, that's the kind of programming in dynamic programming. And the name dynamic programming was something that Bellman made up so that he could get funding. And he didn't want to get in trouble with doing research that was too intense. Even though it was the same research, he decided to put a fun name on it. So the programming was scheduling, and people understood that at the time. And then the dynamic part was literally just a word that was thrown in there because who can argue with something that's dynamic? It's almost hard to think of something that's dynamic in a bad sense. So dynamic programming is this made-up technique name that allowed him to keep funding his research and eventually develop dynamic programming. So memoization is also another part of that. That's part of the dynamic programming that we're going to be doing. Memoization is part of the technique. So we've got this approach that we're doing with our normal recursive algorithms. Generally, we use those to divide and conquer a lot of times. So if you write a recursive version of binary search, for instance, or we know the recursion that's involved in quicksort, both of those are divide and conquer algorithms. And what's important about them is that they divide the problem into smaller problems that we can then more easily solve. And that's what's key about this, is the smaller problems have to, in the general shape, look just like the bigger problem. So for instance, if I'm sorting 50 numbers and I say, well, I'm going to cut that in half, and now sorting 25 numbers looks just like sorting 50 numbers. It's the same work, it's just on less items or fewer items. So that's what's going on with our divide and conquer sort of things. But what's included in that is the fact that my smaller problems, my sort these 25 items and then sort these 25 items, and if all the small ones are here and all the big ones are there, then the whole 50 items is solved. The thing about that is the smaller 25 items have nothing in common with the larger 25 items. Meaning there is no one item that is in both the smaller half and the larger half. Those are two independent subproblems. Not all problems divide into independent subproblems, however. And so when that happens, we can't do divide and conquer, because we can't solve part of a problem and then have part of that problem in another problem with our standard divide and conquer, which is where dynamic programming comes in. Dynamic programming works on these smaller problems. They're congruent problems in the sense that they look like the bigger problem. They just have fewer items or smaller range or whatever, as it's been reduced. They look like the bigger problem, but there may be many of them and they might have some overlap to them. That means our subproblems are not independent. That's where DP comes in. We can solve dynamic programming problems from the bottom up, and we can also solve them from the top down. We'll be looking at both. Much like all of our other recursive things, we can do something from the bottom up, and that's going to mean iteration. or we can do something from the top down, and that generally means recursion. We can use DP when I have some large subproblem that can be broken into smaller subproblems, and the subproblems look like the original problem, and also the subproblems are not independent. So this means that the same subproblem may recur in the course of solving some larger problem. So a really good example is Fibonacci. So we look at solving Fibonacci 5, for instance. Fibonacci 5 needs Fibonacci 4 and Fibonacci 3. Fibonacci 4 needs Fibonacci 3 and Fibonacci 2. So right there, we've got that Fibonacci 3 is part of the solution to Fibonacci 4, and it's part of the solution to Fibonacci 5. So those two halves are not independent, or those two portions are not independent. So that's what we're talking about in this concept of subproblems that are not independent. If I'm able to solve Fibonacci 3, I can help solve a bunch of other problems. And the more often I can use this stuff, the more savings I get. DP will often take some recursive function and completely change its complexity class. That's why we would do it. Something that starts out as exponential can very often be turned into a polynomial thing, and that's pretty impressive. It makes some things that are prohibitive, like you wouldn't even do that because it's so slow. But if you can find a dynamic programming approach to it and reduce that something to polynomial, you can actually get that calculated in real time. It trades memory for speed. That's all it does. It's trading time for speed. It calculates things and stores those values. And later on, rather than recalculating the values, it goes and looks them up and saves time. But it needs memory to hold all of those previously calculated values. This storing of previously calculated values is called memoization in dynamic programming speak. It's derived from memorandum, something to be remembered. It's slightly different from memorization, which is what we do with our memory, but it's got the same feeling. So don't worry too much about it unless you really want to get into linguistics. You can go track it down, but generally, I just refer to the data that I'm storing as my memo. That's where my memo is, and memoization is the act of filling up my memo with the things that I've calculated and also looking things up when I need something. And the bottom line is this is DP. Memoization is DP. I've actually never heard of the word memoization outside of dynamic programming discussions. Doesn't mean it doesn't exist there. I just never used it any other time. A simple approach to memoization is let's take some function that we're going to write. Our first example here was Fibonacci. There's some other examples we'll look at in the future. And when I write my recursive versions of these things, I call the recursive and then I return something. That's kind of the basics of it. So to do memoization, you can do this by rewriting the function just a little bit. So right before I exit, instead of returning that value that I've just calculated, what I want to do is save the value that I just calculated and save its inputs. I need its inputs so the next time I come in and say, here's my inputs, I can use those inputs to look up the value that I've calculated. So right before I exit, I save the inputs and the result that I've calculated. And oftentimes, we don't even actually save the inputs explicitly. I will save them implicitly, like we've done in the past already. And you can do that by saying, well, if I've got this vector of these values, the index into the vector might be one of my inputs. So if I call this with 5, I don't need to save 5 if I've got a vector and I look in position 5 and there's my answer. So you can do this saving of the inputs. Most times that's done implicitly. So if I've got a 1D vector, or if I've got a 2D vector or a 3D vector, those are my inputs, my indices, and I go into that my memo table and pull that value out. So to do memoization right before I exit, I'm going to save the inputs and the result. Then, before I calculate anything, after I've entered the function, I say, well, first let's go check those inputs. Have I already seen those inputs? Because if they have been seen before, that value has been changed. It's something that's non-zero, something that's non-trivial in my memo. And if those inputs give me some non-trivial value, then clearly I already calculated it. Let's just use that instead of recalculating. And so then we just retrieve that. Generally, that happens in constant time. If I've already done the work, I look it up, I pull it out. And you can do this with really minor code changes. Right before I leave and return something, store it. Right before I calculate something, try to look it up first. You can do that on a problem, and you might not even understand the actual recursive function. I could give you a recursive function and say, well, this recursive function actually solves a problem. I would like for you to memoize it. You can say, okay, well, right before I exit, let's store those values, or right before I make the calculations, let's look it up. Well, what does the function do? I don't know, but I do know how to memoize things. Write it, look for it, fix. So here's our Fibonacci example. Let's go in a little bit deeper here. The definition of Fibonacci, of course, we've seen it before. We'll give it to you again. Fibonacci 0 is 0, Fibonacci 1 is 1, and every Fibonacci number after that is the sum of the two Fibonacci numbers before that. So f of n is equal to f of n minus 1 plus f of n minus 2. If I'm trying to find f of 3, for instance, you can see that f of 3 is just f of 2 plus f of 1. F of 2 is f of 1 plus f of 0. And so as I start pulling those things together, you see that I'm making multiple calls to the same functions over and over again. An easy way to implement Fibonacci in 2 or 3 lines here, right? I've got this 3-line version of it. If I is equal to 0 or I is equal to 1, return I, because when I is 0, I get 0. When I is 1, I get 1. Otherwise, just call Fibonacci recursively. Brilliant, isn't it? It looks so nice. It's so elegant. I got it done in so few lines, and everyone understands what's going on. However, this is, as it says, spectacularly inefficient. This recursive algorithm calculates and calculates so many times some things, it ends up exponential here. It's 1.618 to the n. And if you're thinking about what is 1.618, yep, that's the golden ratio. It's right in there. But that's exponential in n, as in if I'm going to get the 50th Fibonacci number, it's 1.618 to the 50th. That's big. So this would work. It's not going to give you the fastest answers, but it is definitely a real Fibonacci implementation. Let's try top-downing this one. We talked about top-down as something that is recursive. So I'm going to be calling Fibonacci from Fibonacci, and that's what we just looked at, a version of Fibonacci that called Fibonacci to get the answers. So this is just a little driver here. You see that we're going to find this 93rd Fibonacci number. And it turns out I'm going to find all of them in between, because my main just takes this for loop and runs from 0 up to max fib. I say max fib is 93. Why do I say that? Because I'm using a uint64t, or something similar to a size t, something that takes 8 bytes of integer data and doesn't have a sign bit. So the largest number I can represent in there is Fibonacci number 93. Anything bigger than that is going to cause overflow, and I have to get to some data type that is not native to C++. So that's why my loop goes here from 0 to max fib. But look at that for loop. We got to get all of this taken care of first. Anytime we've got code with strange things in it, we need to look at it. And what I call strange is a for loop with a less than or equal sign into it. That's strange. It's not my favorite type of for loop. My favorite type of for loop is I equals 0, I less than n, plus plus I. Get it done. But in this case, I've got I less than or equal to n, where n is max fib. How am I going to manage that? Well, in order for me to pull this off, I've got to have enough space to hold all of these values. In the end, I'm going to want to get that 93rd Fibonacci number. And so we're going to end up needing additional space there, and so that's why the less than or equal to is important. So for instance, if I said my container was able to hold those 93 Fibonacci numbers, and it had a vector of size 93, I couldn't go to that vector and say, give me vector square brackets 93. that would be out of bounds, because if it holds 93 items, the indices go from 0 to 92. And I can't get the 93rd one. So in order for me to make this work, I'm going to make a little bit more space. I'm going to have a +1 generally in the dimension that I'm programming. So if I'm programming to find the 93rd step, I need to have a +1. I need to have my container be of size 94, because that way I can take a 93 on my square brackets and get the answer I'm looking for. More on that in a bit. You see, this loop here is going to let me run through 94 times though. And that's important because that 94 times is going to give me the 93rd on a lookup. So that's why the crazy for loop there. And that is crazy. Other than that, all I'm going to do is print out this call to some function called fib of I. And that's on the next slide. So there's our setup, and we can go for it. Here is my top-down fib. And if we remember the previous version, my naive implementation that I said was spectacularly inefficient, you'll see all of those things here, right? I've got some base case that lets me get out. And I've also got this recursive call here in line 30. Fibs of n, I'm going to store in there now fibs of n minus 1 plus fibs of n minus 2. So there's my two recursive calls from the original inefficient version. I've got to find where my base case is in there, right? And so I've got something here that's going to let me get out without recursing in line 26 and 27. So it says, if what's in my memo at n is greater than 0 or the number is 0, then just return. So we'll talk in a second, but this is my base case. It's a recursive function. I've got a base case here, and then right before I leave, I store what I was going to return. You see, I return it in line 31. So in the previous version of this function, I just said return fibs of n minus 1 plus fibs of n minus 2. Instead, now I'm going to write that into some memo, and that memo is declared right here in line 19. That memo is called fibs, and I mentioned earlier it was going to be of the size that I can count plus 1. So this is max fib plus 1, which gives me 94 items in this array of uint 64s. Why do I have 94? So at the end, when I want to return fibs of 93 down there in line 31, I can put a 93 in there for n and not go out of bounds. That's what's going on there. Still more. Line 19, static uint 64t fibs of size 94, right? So fibs is an array of uint 64 types, but it's also static. And what static means is this data belongs to this function. And every time I come back into this function, I want that data to still exist. So normally we think of a variable inside of a function as living in its stack frame, and then when the stack frame gets popped, all of that local data goes away. Static undoes that. Static says we're going to put that data somewhere else, so the next time you come into this function, those data still exist. But the very first time you go in there, we're going to do whatever initialization step you give us, but after that, we do not need to initialize it. So here in 19, it says, let's declare fibs and set it equal to curly brace 0, 1 curly brace. So I've got 94 ints. I put the first one in as 0. I put the second one in as 1. If you remember, those are my base cases. And then all the rest of them get initialized to 0. That's important about the C++ syntax here. So 0, 1, and then imply the rest of them means give them a 0-based initialization. So after line 19, the first time I call fib, it's got 0, 1, and a bunch of zeros in it. Every time I come back to it again, it does not reinitialize it. It just keeps it as what it had. So you see then, when I call and come out of fibs down here, right before I leave, come out of fib here, right before I leave, I write into fibs. And then the next time when I come back into fibs, into fibs still exist. They still have the values that I previously calculated. All right? So here we have it then, is my lookup step. I can see that I've initialized it to mostly zeros, except for that 1, 1, that's at index 1. So then anytime I hit this line 26 that says, if fibs at n is greater than 0, I'm either looking for the first, the 1 Fibonacci number, or if I've already calculated it and it's in there, this will find and return it instead of recalculating it. So this is a little bit involved, but it's using a couple of techniques that it's important to know that they exist, and a little bit of good planning to figure out how I can do this. You can do this in another way. If you wanted to write this in a class, then you could maybe keep this static fibs as a member variable. There's different approaches to this. This one is a pure C version of it that works out pretty well in C++ as well. So that's Fibonacci top down. What it's doing though is here in my main loop, I went back a slide here. Here in my main loop, I've got this 0 up to max fib. So first it says, let me look up fib 0. Well, when n is equal to 0, it returns 0. Then it says, let me look at fib 1. It says, well, if what's in fibs at 1 is greater than 0, return it. And we know it's 1 because we put that in there. Great. The next time it comes to line 9 here, it says, how about when I is 2? It says, well, let's go in there and call fibs 2, or fib 2. Fib 2 looks at fibs 2. Fibs 2 has a 0 in it. So then it says, I guess I've got to do the work. It makes a recursive call and gets the 1 that on a lookup, and makes another recursive call and gets a 0 on a lookup, both of which take a constant amount of time, and then fibs 2 gets calculated in a constant amount of time by adding those two values together. It writes the 1 into that 2 index of fibs, and now I've got 0, 1, 1 in my Fibonacci container, fibs. The next time I call it with fibs 3, it looks up a 1 and a 1 in constant time, adds them together in constant time, and puts a 2 into the fibs container. Then when I call it again, it looks up a 1 and a 2, adds those together, and puts that in there. So each time I call this as I move down the line with this for loop, because this for loop is increasing from 0 up to max fib, I'm going to do a constant amount of work. I just look up the two values before me, add them together, and write it down, and return it. So in this case, we've taken something that was exponential to now something that looks like it's constant time. It's not exactly constant time because all of the other ones have to exist for me. So this one ends up being actually amortized constant, because if you call fibs of 50 and then later on someone says, well, give me fibs of 40, you can look that up in constant time. The first time to get to fibs 50 takes me a linear amount of time to get there. If I want to calculate fibs of 60, it takes me a linear amount of time to go from 50 to 60. But then everything from 60 down to 0 is still available in constant time. So this is how memoization often works. It can take something that was exponential and turn it into something linear at worst, maybe even amortized constant at best. To be honest, I wouldn't probably apply DP to use Fibonacci. Fibonacci, there's better ways to calculate Fibonacci than to use DP. But this is a great way to explain DP because we already have a fundamental understanding of Fibonacci numbers, and it does work as a technique for Fibonacci. So then this question is, how does this improve from the normal recursive implementation if we're not looping from 0 to 93? If we're not looping from 0 to 93, it still makes it linear. So if I'm not looping from 0 to 93 and I just had that version and I say, give me fibs 51, right? It's going to calculate all of those up from 0 to 51 and store them all and then return the 51 value. If I never make another call again, it still took me linear time in 51. If I make a call less than 51, I get that in constant time. If I make a call greater than 51, I get that in linear time from 51 up to where that is. So it is still definitely better than my exponential version because it gives me at worst something linear and at best something in constant time if I've already done it. So yeah, pretty slick. This is a version of Fibonacci bottom up. We can see that it's completely different now. With this function is called fibbu, and there's no evidence of another call to fibbu. Great. All we have in there is this for loop in lines 6 and 7. Everything else looks to be some declaration or simple assignment or a return statement. So it's really easy to look at this piece of code and say, oh yeah, this is linear. There's just a for loop in there. And all we do in this one is we do something similar where we get some array of uint64t's. We see this, call this max n there. And what we're going to do is just go through there and fill in those values, right? So if I start with 0 and 1 in f, then I start looping from 2 on, I can just say f at k is equal to f at k minus 1 plus f at k minus 2. And I just add those together and write them down. So this version of the bottom up is clearly linear. We're writing things in there, and then I return them. This one doesn't have the static thing, so every time you call this, it does a full linear calculation of the value that you're looking for. Not the end of the world. But you can see that I can do this both top down and bottom up. And in general, when we're doing these things, it's important to note that these things are always solved from the smallest value up to the biggest value, even if it's called differently. So bottom up is very clear. We're taking the smalls and we build them up. Top down is not as clear. It asks for the big, but then asks for something smaller, which asks for something smaller, which asks for something smaller. It doesn't stop asking until it gets down to a bottom level solution and says, base case, oh, we've got that. So we always end up solving this from our smallest value up to the biggest, even when we call it bottom up or top down. So that's important to remember. We save all of our previous values here, and we can see that the values in this f, they grow exponentially like Fibonacci numbers do. All right. This now has taken dp and gone from something that was exponential to linear. And that's impressive, right? That's a polynomial of order 1. We said we could go from exponentials to polynomials, and this has done exactly that. Yes, we'll talk about some memory savings later. That's a great insight there. Joseph and William got that one right on the nose there. We'll come back to filling that in a bit. So here is my binomial coefficient. New problem, something else that we are also going to use dp to solve. This one's a little bit better for why I would really need dp to do it. So here's my definition of the binomial coefficient. That's n choose m. If I've got how many ways can I choose these n things from a collection of m of them? So I've got n factorial divided by m factorial times n minus m factorial. That's how I would calculate it. That's really nice. We can see that as something that is fairly elegant. N factorial divided by m factorial times n minus m factorial. That's great. There's a problem with calculating it, however, is if I were to just write factorial, that's fairly easy to do. I know that n factorial is just n times n minus 1 factorial. So I could write that recursively really nicely. Say factorial of n is just n times factorial of n minus 1. Or I could write it iteratively and start multiplying up until I get to n. Either way, I could write factorial without too much challenge. I could solve for n factorial, then I could solve for n minus m factorial, then I could solve for m factorial and just multiply and divide and have my answer in the end. This works great with math. It does not work great with computers because of integer overflow. Factorial numbers are huge. 13 factorial, for instance, causes overflow with a 32-bit integer. So if you just say int and then try to calculate 13 factorial, you will have overflow and you will not get the right answer. You say, well, okay, well, let me do a uint, because now I'm unsigned. I know I'm going to be negative, so I'm going to use the full 32 bits there. I can't get much bigger there. At 64 bits even here, I can get 21 factorial, which is not that large. At 128-bit integer, I can only get to 35 factorial. So think of something simple like, how do you calculate the total number of poker hands? Well, there's 52 in the deck, and I want to choose 5 of them each. So 52 choose 5. Well, I can't calculate that because n factorial is 52. I can't calculate 52 factorial. I can calculate 5 factorial, but I can't calculate 52 minus 5. I can't calculate 47 factorial either without overflow, so I can't calculate this number. You say, well, maybe the number of poker hands is so large you can't store it. Turns out there's only 2.5 million different poker hands. So a number that I should be able to calculate because I can represent it in my data type, I can't calculate with this naive approach because of my intermediate products causing overflow. So what do we do about that? We ask our friends at 203. Is there a better way to calculate the binomial coefficient? And of course, they come up with something amazing because that's what 203 does. And this is why we all know and love 203, because they do so many amazing things. But there is this new way to write the binomial coefficient, and that's recursive. So here's how I'm going to rewrite the binomial coefficient, right? My binomial coefficient with the recursive definition at the bottom says that n choose m is just equal to n minus 1 choose m minus 1 plus n minus 1 choose m. So there's n choose m written in terms of n and m. I need some base cases. Of course, we can't recurse without base case. How could we possibly even think of recursing without a base case? It's all about that base. It's all about that base, the base case, right? So there it is, n choose 0. So I've got all of these items. How many different ways can I take none of them? Well, there's only one way. You don't take anything. How about n choose n? How many ways can I take all of them? There's only one. You take them all. So those are my two base cases. N choose 0 is equal to n choose n, which is equal to 1. With that, I can take this recursive definition and solve for any other n choose m recursively. This is good? Question mark. You've added recursion where we didn't have it before, and that's an improvement? Well, let's just try to write this. This is easy enough to write. You can look at the base cases here in lines 2 and 3. If m is equal to 0 or m is equal to n, that means if I'm choosing none of them or I'm choosing all of them, return 1. There's my base case. And then binomial coefficient top down calls binomial coefficient top down again in lines 5 and 6 with the recursion. It looks just like the previous version where I'm returning binomial coefficient n minus 1 m minus 1 plus binomial coefficient n minus 1 m. Those are the two ways that I add this up. And you can see here, this is incredibly elegant. It's a direct translation of the previous mathematical version of this. So simple, so direct. So in terms of elegance, I'm going to say yes. In terms of efficiency, this is that poor exponential thing that's going to just drive you into waiting for the sun to cool while you're waiting for your big answers. So this is not efficient, but it is elegant. Let's see if there's a way to fix that. Let's go binomial coefficient top down, but we're going to memoize this thing. Okay, so we said the first step of memoization was rather than just return a value, write it down first, then return it. So what used to be return these two calls the binomial helper now turns into write that value into memo at mn in line 9 here, and then return it. So write it down first and then return it. That's the first step of memoization. And the second step was when you get here, before you bother doing the calculation, look it up. Here in line 7, it says if memo at mn is greater than 0, which means somebody's already calculated before. If it's already calculated, just return it instead of recursing. And that's it. That fixes the whole thing. The rest of this is mechanics of how to get this put together. We'll talk about it, but that was what it was. We took that previous one that was elegant and horrific, and with just a small little tweak, we've made it very nice, right? So what we've got here is our original base case. If m is equal to 0 or m is equal to n, then I'm going to put a 1 in that position and return that 1. Just like here, I was putting a value into that mn and returning that value. So this is one of my base cases. There are plenty of base cases in this case, because if I've got, for instance, 15 choose 5, I've got to check out 15 choose 1, I've got to check out 14 choose 1, I've got to check out 13 choose 1, I've got to check out 12 choose 1, and so on, all the way back to 1 choose 1. So those are all base cases that need to return a 1. I also have to look at 1 choose 1, 2 choose 2, 3 choose 3, 4 choose 4, 5 choose 5, and so on. So all of those are base cases. I need to put my values in there. So in this version of it, we're passing in this 2D vector here, which is the memo. We're passing it in by reference because we don't want to make copies, and it's not going to be constant because we're going to be making some changes. So that's my third parameter. I'm passing in the memo as a 2D vector by reference. I make some changes to it, and then I just return. So what I'm calling it with is n and m and the memo. That's what's going on down here in my overall function call to binomial top down. Binomial top down sets up the proper size memo and then calls the helper function, which is the one that continues to recurse and recurse and recurse. All right. So what else is nifty about this solution? Remember I talked about having the ability to square brackets at the value that I wanted, right? So now if I'm saying n choose m, I want to square brackets at n, I want to square brackets at m. That's going to make it happen. The only way to do that is if I've got enough room to do it. So you see here in this declaration line 15, I've got this 2D vector, and the size of the 2D vector is m plus 1 by n plus 1. Right? So this lets me go from 0 up to m and 0 up to n. That's very important because the very last line of my helper function, which gives me the final answer, is a return of memo square brackets m, memo square brackets n. That returns it. So if I couldn't square brackets at that location, I would have a problem here. This is why the plus 1 in this declaration in line 15. All right, so this is my lookup here in line 7 and 8. If I've already calculated a value, because it's greater than 0, you see here that I didn't initialize it. I should probably make it clear that these are all zeros. I could do that with another comma 0 over there. But for now, we know that this thing is all filled with zeros, and I'm going to be putting 1s in there where I need the things that I'm going to use, and this is what gives me my answer. So this is the top-down binomial coefficient with dynamic programming. We've got a memo that we use, and it saves us a ton of time. Here's binomial coefficient, bottom up. What's the difference? There's no recursive calls. There's just loops. So I've got this two-dimensional memo that I used because I was putting in a two-dimensional vector. So it's not unreasonable to think that I've got two nested for loops. I've got a for loop that fills out my rows and a for loop that fills out my columns. So I'm going to work my way through each one of the rows and work my way through each one of the columns. You can see the other elements that we are used to. I've got my base case there in line 5. If I is equal to j or I is equal to 0. If I'm choosing all the items or if I'm choosing none of the items, there's only one way to do it. It's 1. That's setting c at I, j equal to 1. And then as I get inside here, lines 8 and 9, that has my other sort of lookups that say to fill out c at I, j, I just need to find c at I minus 1, j minus 1, and c at I, j minus 1. Great. So if we're thinking about the way we should be doing things here, we can know that our i's are giving us different rows, and j's are working through my columns. So what this means is when I fill out C at ij, all I'm doing is I'm looking up one row and one column to the left, that's Ci minus 1, j minus 1, and I'm also looking in this same row, Ci, at j minus 1, one column to the left. So every time I write a value here at Cij, I'm adding up two values, one just the previous in this row and one right directly above that previous in the row before that. I take those two values, add them together, and this solves my binomial coefficient problem. In the end, I'm able to do what I always like to do, just return C of m and n, because I can look it up, and you can very clearly see from the way that this function is constructed, I've got two for loops. I got a for loop inside a for loop, and the one for loop goes up to m, the other for loop goes up to n, you multiply that together, this is big O n m. Got it. Once again though, let's make sure we get a look right at those things there. Those are for loops with less than or equals into them. You've got to be careful. Whenever you see those, whenever you write those, make sure there's a really good reason. There's a great time to put a comment in your code if you ever do a for loop that has something other than I equals 0, I less than n, plus I, or something like that. Right here, these less than or equal to's are because I've got that plus 1 in both of those directions. C is size m plus 1, n plus 1. And I need to be able to hit all of those, and that's what the less than or equal to does. All right. That is the binomial coefficient. I strongly suggest you practice that one. Go back and play the computer, which is where you give yourself a value to calculate, and you write the loops out on paper, and you update your i's and j's, and you write down the actual two-dimensional vector that is your memo and start filling in those values and see how they work. As a general approach, the top-down saves known values as they get calculated, and we like this one because it's easy to sort of find the natural recursive solution. So if you can find the natural recursive solution, writing the top down is usually pretty straightforward. You take the recursive solution, write a recursive function, and then you memoize it. It helps us because it will calculate the subproblems in the right order. Sometimes the order that they get calculated in is important, and sometimes you don't even need to calculate all of them. That's one that we would see if we were to do binomial coefficient, for instance. It's not something I can get away with on Fibonacci numbers. There's no way for me to calculate fib 50 without having calculated all of the fibs before it. Whereas it is possible for me to calculate some binomial coefficients without calculating all of the other binomial coefficients. And top-down would find that. I think I've got an illustration of that here coming up. So our top-down approach is adaptive. It only computes the values that it absolutely needs, whereas the bottom-up, because it starts at the bottom and calculates everything small all the way up to big, it calculates everything. Sometimes you might calculate even more than you need in getting what you really want. So the general approach for bottom-up, this is the one where we use the iteration. This pre-computes the values from some base case up towards the solution. It's loosely non-adaptive because it does calculate all the smaller cases, whether you need them or not, because it doesn't know. It just is more like push versus pull manufacturing. We just make a bunch of parts and hope someone uses them. Sometimes you make more parts than you need, but if somebody says, I would like an order of 50 parts, that's a pull, and you make those 50 parts, you never have more parts than you need. So that's the difference between sort of bottom up and top down. So bottom up is just, let's push them out the door. Top down is let's fill exactly the orders that we've been given. We've got some nuances. Bottom up can always be used anytime top down can be used. You can be assured that when you have a DP problem on the final, and you will have a DP problem on the final, that's problem number 25 or 26, it's usually 25. But that's a DP problem. You're going to have to do one of these. And the ones that we'll give you, you can write either top down or bottom up, whichever works for you, whichever way. Sometimes problems are easier to think of a solution top-down or bottom-up. We've got a lab 10, we're going to be doing some DP stuff, and that one for me is just loads easier bottom-up, and every time I think about it top-down, it's hard on my head. It can be done, but it's more confusing to me to think about it that way. I've done it, but even when I've done it once and I think about it again, it's harder for me to think of that one top-down than it is for me to think of it bottom-up. So you'll use what's available to you and what makes most sense. That's good. We have to be aware that our time and space requirements for DP are a concern. We're trading time for space, right? We're getting a speed up because we're writing more things down. There's got to be some upper limit on how much we can write down, so that's what's important. When we're using the memo, obviously that's going to be storing information in the memo. When we're writing bottom up, we've got this iteration going on. That's pretty straightforward. We're all in one function call. We've got one stack frame. When we're going top down, we're still using the memo, and we might also be using multiple stack frames as we recurse into smaller versions of the problem. So be aware that memory is an issue. Bottom-up approach can also do some recycling or collapsing. We saw that earlier in a suggestion from, I think it was William and who else was on that? Joseph, right? So as we're thinking about calculating, for instance, the Fibonacci number, if we're going from the bottom up and our goal is just to get to one particular Fibonacci number, I don't need to have all of them later. If I just want to get one, I don't need to have more than two values. I take a 0 and a 1. I add those two together and overwrite the 0. I swap them. Now I've got a 1 and a 1. I add those two together and overwrite the 1. Now I've got a 2 and a 1, and I swap them. Now I've got a 1 and a 2. I add those two together, I get 3, overwrite the 1, and I swap them. I've got a 2 and a 3. I add those two together, I get 5, overwrite the 2, and I swap them. I got 3, 5. And so you can see that there's a way to save some memory. I don't need to have the entire vector. And that works for a bunch of my DP solutions. So as we were writing the binomial coefficient, for instance, we were filling out an entire row, and then we worked down a row. And every time I filled out a row, I needed something earlier in my current row and something in one row above this. That was all I needed. So when I'm down 15 rows, I only ever look at values in the 15th row and the 14th row. So if you're a little tricky with your programming, you say, well, I only ever need 2 rows, the current row and the previous row. I can save and write things from the previous row and total them up into the current row, and then if I did a swap, then maybe now my old current row turns into my new previous row, and I just add things there. So you can get some memory savings when we're going these bottom-up ones because they can recycle the things that you're using there. That's a pretty interesting approach, memory savings. Top down or bottom up. I mentioned any problem we give you, either solution should work, top down or bottom up. Some problems, the base cases are easy to see, but the ones just above that are hard. Some problems it's hard to see which subproblems need to be computed. But if you get the approach, you find a way to get one of them done, that's a good start. So for instance, as I'm talking about, I got a question here, why would top-down not compute all of the cases? So if we think about the way that the binomial coefficient works, it fills out this first row when we're going bottom up. Fills out the first row, 1 choose 1, 2 choose 1, 3 choose 1, 4 choose 1, blah, blah, it's a bunch of ones. Then it fills out the second row, and it's based on things in the second row and the first row. It adds those things up, and it fills out from 2 choose 2 to all the way over to 15 choose 2. Then we go down to the third row, 3 choose 3 all the way to 15 choose 3. We go down to the fourth row, 4 choose 4 all the way to 15 choose 4. Right? So I filled out the entire sort of square memo that I'm filling out, except for that small triangle where it doesn't make sense. How many ways can you choose 5 items out of these 2? That doesn't make sense. Can't do it. So that little triangle at the beginning is a bunch of zeros, but the rest of it gets filled out. But let's go back and think about how top-down would do that. So after I fill out the first row, second row, third row, fourth row, fifth row, say I'm doing 15, choose 5. In the fifth row, I start at 5, choose 5, 6, choose 5, 7, choose 5, 8, choose 5, 9, choose 5, 10, choose 5. I get all the way out to 15, choose 5. Great. Now I've got it done because to get to 15, choose 5, I needed 14, choose 5. And to get to 14, choose 5, I needed 13, choose 5, and all the way back. But what does top down need? Top down at 15, choose 5 says, I only need 14, choose 5, and 14, choose 4. So let's get those. And then 14, choose 5 can start to pull things from this, you see this diagonal band that ends up running because I only need the one item in the row before it. And so then I can get those values from over and up, over and up, over and up, and over and up. And so if I go and do this from the bottom up and I'm not careful, I'll have basically this 2D memo completely full, except for that little irrational triangle. Whereas if I start from the top down, I just get this band that's 3 wide that goes through there. I don't have that. I'll pull up the tablet here if I get a few more minutes at the end of this to make that a little bit clearer. But DP is this advanced technique that helps us solve problems. It trades space for time, and it can only be used when my solution domains are dependent upon each other. I've got to have this overlapping subproblem things going on. We've got the bottom-up approach, which iteratively pre-computes everything, and then a top-down approach, which recursively computes and saves only the things needed. Both versions get to the solution by extending from a base case upwards, though. So that's DP. I've got another example here. We're going to look at a new one. This is solving the knight moves problem using DP. In this one, if you've played chess or known someone who has, you might understand how some of the pieces work. If you don't, there's the only piece we're using. It's the knight. The knight has this rule for traveling that it can move 2 in any direction, turn 90 degrees left or right, and move 1 more. So this little 5x5 area here shows how a knight standing in the middle there in black can make it to any of these 8 spaces that are these grayed out future places where the knight can move in 1 step. Does that make sense? Hopefully you get that, right? If you've already played chess or done any sort of learning of chess, I can't play chess to save my life. I do know how knights move, however. I know how all the pieces move, I just can't put it together. So, knight moves here, we're going to be trying to solve a problem by using a knight. And here's the problem. Moving from the top left corner, that's up here, down to the bottom right corner of a standard 8x8 chessboard can be done in 6 moves. It can be done in more, but it can't be done in fewer. So the question is, if I can do it in 6, how many different ways can I do it in 6? Right? Because you can understand that I can move down first and then across, or maybe I move across first and then down, or maybe I move across a bit and then down some more, or I'm going to move across most of the way and then all the way down, and so on. There's a bunch of different ways I can get there. And the question is, how do I count how many ways I can get from that top left corner to the bottom right in exactly 6 moves? Let's use dynamic programming with a 3D memo. The 3D memo is going to calculate all the moves from the beginning all the way to the end after 6 moves. This is an example of what this might look like. We start out at the top left corner here. After 1 move, this red knight can go to either of these 2 black knight positions. That's possible after 1 move. On the second frame over there, you see that those 2 places that could be after 1 move, that's in the 3rd row, 2nd column, and 2nd row, 3rd column. Those are the 2 places where the knight can be after starting in the 1st row, 1st column. Those are the grayed out positions because they can each reach the other black locations that are all 1 knight's move away from the gray areas. And you see in the top location in 1-1, there's 2 knight's heads there because there's 2 ways to get there. I can start at the beginning and go through the gray knight in row 3, column 2, and then return, or I can go through the gray night in row 2, column 3, and then return. So after 2 moves, they're gray night positions. So I can get to both of those 2 different ways in 2 moves. All the other single black knights mean that there's only one way to get there after 2 moves. You should be able to track those down if you understand night moving. If you don't, take another break here and sort of grab a chessboard, figure it out. All right, so that's what we're trying to do. And this lets us see the overlapping subproblem. Here in this 4th row, 4th column, I've got a black knight, and I've also got highlighted the 3rd row, 2nd column gray knight, and the 2nd row, 3rd column gray knight. Those are my overlapping subproblem. So calculating any path that goes through the black knight could come through either one of those 2 problems, and I don't want to have to recalculate that anytime someone else needs the answer to the black knight question over there. How do I get to 4-4? Well, you could have gone through 3-2 or 2-3. So there's my overlapping subproblem in the knight moves problem. All right, let's drop all the horse heads and start putting some numbers in there. So now I've got some visualizations of my memo. And what that is just a 2D vector of where I'm going to put some numbers. I've got memo 0 here in this first one. And what I'm going to say is like, how many different ways can I be at a particular location? So memo 0 represents the ways I can be in any one of these locations after 0 moves. Since I start in the top left corner, that's the only place I can be after 0 moves. There's one way to be there, that's the start. Everything else that's not filled in is just me saving digital bits, because that would have been full of zeros. But you can think of there's 0 way to be in row 4, column 1 after 1 move, because we have to start in 0. We have to start at the top. So that's what's going on here. You can see the top left corner of my chessboard. I've just done the top left corner in these early 2 moves because I can get 2 of them on the screen at the time and you can sort of see the travel there. So I've got a 5x5 of memo 0, even though it actually fills out to 8x8. I've got a 5x5 of memo 1, even though it fills out to 8. So I've got 1 in the top left corner of memo 0, 0. Memo 0. All the rest is full of zeros. In memo 1, which is all of the places I can be after 1 step, and how many ways I can get there, I've got that 1 in row 3, column 2. I've got the 1 in row 2, column 3, because if I start at this place in memo 0, I can get to those 2 places with 1 step. Everything else in memo 1 is a bunch of zeros. Save the bits again. You see, I didn't even have to put the black bits on there. It's like cheaper than putting the white bits and the teal bits. Okay, I'm being silly. You got me though. Hopefully. So that's memo 1, and it's got a bunch of zeros in it, but 2 1s, because there's 2 places I can be after 1 move, and for each one of those places, I can get there one way. I can start at the beginning and go down 2 over 1, or start at the beginning and go over 2 and down 1. That's where I can get to. This now is what memo 2 fills out. Memo 2 shows the places I can get, and this should look familiar to you. We had the previous version with the 2 horse heads that were in row 1, column 1, and the 2 horse heads that were in row 4, column 4, and then the rest of those other black ones are the ways that I can get to those locations after 2 moves. Remember, we're looking at memo 2, which says, how many ways can I be at every one of these locations after 2 steps? Everything that's not filled out is a 0. You can see the 2 gray ones, which are actually from memo 1. They're just in gray so that you can see them there. They're not really a part of memo 2. It's important to note here that the gray ones from memo 1 are on white, and the black ones from memo 2 are on teal, because every time a knight moves, it goes from one color to the other. You can't have one move from teal to teal for a knight, or from white to white. So all of my memo 1s had information on, or non-zero information on white, All of my memo 2s can only have non-zero information on teal, because there's 0 ways after 2 moves to be on any white square. Great. So let's take those 2 from memo 1 out, and we just got a nice clear version of what is going on in memo 2 only. These are the only places that I can reach, are these teal ones with values in them. Everything that has no value here is a 0. There's 0 ways to be farther away from the beginning here, even on teal with only 2 moves. There's 0 ways to be on any white space after 2 moves, because it doesn't work that way. All right? How do we get these values? Let's break this down a little bit. There is an 8 here, and this is going to be in memo 3. And we see that memo 3, remember, allows us to write on the white spaces, and it writes on the white spaces by adding things up that were in the teal spaces that are reachable. So in this second row, third column, I've got an 8 because these values that are here in the purple can all reach it. So that's 2 from the first row. I got first column and fifth column. They can both reach second row, third column. I've got 2 from the third row. That's first column, fifth column. They can both reach the second row, third column. And then there's 2 from the fourth row in the second and fourth columns respectively, because all 6 of those spaces can reach that second row, third column. And if you add the values up, I've got a 2, a 1, a 1, a 2, a 1, and a 1. I add those all up, that gives me 8. So what I'm going to do throughout the rest of this is fill in every location just this way. Find the up to 8 values that can reach it, add their values from a previous memo, and put them into this memo. So here the memo 3 filled in 8 by adding things from memo 2. Good? Anything else that can't reach it doesn't contribute. Anything that would be a 0 can still contribute 0, and we'll see that in a bit. There you can see some symmetry that's going along there. So we've got the same value 8 in row 3 column 2 as we had in row 2 column 3, because there's a different set of things from memo 2 that contribute to it, but they end up having the same values. All right. This is the full memo 3 now. Memo 2 is still included in gray, so if there's any one of these locations that you would like to figure out how it got contributed to, you should be able to track down a black value and go to the areas around it that could contribute it. So for instance, in this third row, fourth column, I've got a 4. It was contributed to by things in the second column, in the second and fourth rows. We see that there's a 0 because there's 0 ways to be at position column 2, row 2 after 2 moves. Impossible to be there, so that contributes a 0. So I add that 0 and the 1 in row 4 column 2. Add that up, and I can see that that 4 is also contributed to by the values in the first row here in columns 3 and 5. There's a couple of 1s there. Those add up to 3 of my 4, and there's one last 4 here down in row 5 column 3, that all 4 of those 1s add up to give me that 4. You see, there's some other things that might contribute to the 4. Like if I go into the 5th row, 5th column, that could reach that position in one night's move, but I can't get to the 5th row, 5th column in 2 moves, so that's still a 0. So that contributes 0, much like second row, second column contributes 0. All right? Excellent. So now we can continue to work through our memos. Here's memo 4. it's got all of my teals. So after 4 steps, I can be back to the start 16 different ways. I still can't, however, reach the bottom right-hand corner. That one has got no value in it because it's impossible to get that far in 4 moves. So that one's still 0. I go to Memo 5. This fills in all of the white squares. This is the first time all of the white squares are filled, because after 5 moves starting in the top left corner, I can reach every white square on the board. What about Memo 6? Before we go to the slide, what's it going to be? Memo 6 in the bottom right corner comes from 1 row up, 2 columns back, and 2. That 54 plus 54 gives me 108 ways that I can go from the top left to the bottom right in 6 steps. That's the most efficient way to get there, and there's 108 different efficient ways to get there. I can't go any shorter than 6, but there's many ways I can get there in 6. So that is night moves with dynamic programming. Let's talk about it a little more. What is the time complexity for this solution? Feel like we have this memo, and the memo is 8 by 8, obviously for every board. But in order for me to get 6 moves in, I need 7 boards. So the time complexity involved me filling out basically the majority of every one of these 8 by 8 memos, and there were 7 of them. So I would say that the time complexity for this solution was 8 by 8 by 6. 7, but that was initialization. We didn't have to do anything in the 0-base version of it except put the 1 in the top left corner. So really we did 8 by 8 by 6, which is the 6th step here. So if I were to generalize that and say, well, how can you do this in a board of size 40 by 40 in some number of moves there, right? You can say 40 by 40 by the total number of moves. So n by m is the general time complexity. The memory complexity is similar if we do it simply. If I do it simply, I mean if I've got one board for every step, like I talked about having my memo, which was 8 by 8 by 7. So that's got a board for the 0 move, I've got a board for the 1 move, I've got a whole board for the 2 move, and you can look at that and say, well, there's impossible for me to even use half of that memory. It's impossible, because I can't be on a white square on an even move, I can't be on a teal square on an odd move, so that's just wasted space. Well, yeah, you could. You could find a way to collapse this down so that I was only writing on the teal spaces in this board and only on the white spaces in that board. You say, well, I could collapse this down, and with a bottom-up version, I could actually solve this in n by m time, but in n by n memory. Whoa, try that. I strongly suggest you take some of your copious free time. We all have so much. But if you can scrub up a half an hour, try to write night moves, bottom up. It's pretty straightforward bottom up. Try to write it bottom up, real straightforward, no optimizations. Just write it, get it working, get it done. Then if you want to go back and see, well, how can I optimize this so that I only add things from here or there when I need to, or I only use this much memory than I need to. Then try writing it top down. It's a bit more complicated writing it top down. You need to not get caught in an infinite loop because, you know, row 8, column 8 needs something a little bit higher, but it thinks it needs row 8, column 8. But you can't answer this before you answer that. You don't want to get stuck in an infinite loop. You got to do a little bit of thinking to get out of that one. So, describe the top-down method if you can. You're asking for this bottom corner. I'm asking for row 8, column 8. The only way I can get there is if I've got the answer to row 7, column 6. And if I've got the answer to row 6, column 7. The only way I can get those is if I've got some other things. And so those are going to make their own recursive calls to get the values that they need. And they all have to make the recursive calls to get the values that they need. So that is how the top-down method might work. Make sure you understand it, because this was definitely bottom-up. When we've got loops, you're thinking bottom-up. All right, that was night moves. I've got, I was going to show you how to do this on my tablet, but my tablet is currently the camera that we're using. So I'm going to wrap this up into something like that. We'd have to use a different camera. I'm not sure that's going to work here in the live studio. So let's see if we can answer any questions. The way we did night moves is bottom up. Yes, that's correct. How will we do this? Top left and then the search. Top down and then the search at the top left. Yes. Top down means start from the answer and ask your way all the way back to the base cases. Excellent. Okay, so as I mentioned, we will be doing a DP problem on the final exam. I have not looked at it yet. I didn't want to give anything away. So I can look at it now safely after this lecture. I won't feel like I forgot something or added something that was unfair. My suggestion is dynamic programming takes practice. It takes practice. It just takes looking at it. It is not really a difficult thing, but it ends up being high stakes on the exam because all DP solutions are about a trick. You have to see the trick that relates the things that are important. If you don't see the trick, you cannot solve the problem. It just doesn't happen until you can see that recursive relationship. So for instance, I like to talk about this one. In the middle of the lunch ticket saga, say I'm on day 6, punch 4. When you realize that there's only 2 ways to get to day 6, punch 4, that's day 5, punch 4, day 5, punch 3. That's the recursive part that can be hard to see. It can be especially hard to see sometimes when you try to build this up from the base case. A lot of times you might end up writing it up bottom up from the base case, but while you're trying to understand, while you're trying to solve the problem in your own mind to get the recurrence relationship that is fundamental to every DP problem, even if you're not writing recursively, there is a recurrent relationship that is important. It's often easy to just start in the middle. Start somewhere in the middle and say, well, how could I have gotten here? Right? So just thinking about Fibonacci, like, how do I get to Fibonacci number 28? Well, I just needed Fibonacci 27 and 26. Oh, and there's the recurrence. I need to find these 2 previous values and add them together. When I'm looking at trying to calculate a binomial coefficient, I say, well, how do I get to this place? I need the one to the left of it and one diagonally up and to the left by 1. If I've got those 2, that's the recurrence that exists in my memo that I need to combine to get to my value. There's 2 different major reasons why we use DP. The ones we talked about today were all sort of enumerations, countings. We counted to a Fibonacci number. We counted the number of ways that I could calculate the binomial coefficient. We counted the number of ways that I could move a night from X to Y. Another way that dynamic programming problems are used is through optimization, right? I need to optimize how is the fewest number of ways I can do X, or what is the tallest thing I can get out of putting these things together, or something like that. So DP problems do either enumeration or optimization, and so your optimizations can go either way. So there's DP problems that do minimizations, there's DP problems that do maximizations, and then there's DP problems that do enumerations. So my suggestion is make sure you check out some online resources about DP. Learning about it once is never going to work. It's never going to be good enough. I've read about DP. It's one of my hobbies is finding new textbooks that discuss DP so I can read it again from some other author's point of view. So you probably should see another 2 or 3 authors if you can, and maybe that's just another YouTube video, or maybe you go to a walkthrough at LeetCode or some other site that's similar, but you need to see more DP problems to really get a grasp of this, because I promise you, you'll think, okay, I got it, because you understand the one that was just explained. And then you get the next problem, which is unlike one that you've ever seen before, and it literally feels like you know nothing. You have no place to start. You've got no answer coming. And so you need to see more DP problems. You need to see more DP approaches. So my suggestion for people always to study for the final exam, since it's 20 good solid points, is go see a bunch of DP solutions. Go see the problems on LeetCode. Think about it for 5 minutes. Try to see if you can figure out what the recurrence is. If you can, great. See if you can take that a little farther. If you can't, think about it, think about it, think about it. Then just go look at the solution code. Look at someone else's solution to it and see how they constructed their memo. See how they filled out their memo. And then the next time you got a DP problem, that's what you're going to do. Most of the time in DP, a good way to think about this is from the end or somewhere in the middle, right? To say, if I'm going to add these things together, what's the best I can do before I take the last step? Because if I take the best before the last step, I can extend this only a limited number of ways, and that's a really good way to do it. We'll talk a little bit more about DP in the next lecture. We're talking about the knapsack, and we'll solve the knapsack problem, which is an optimization using dynamic programming. You'll also have the lunch ticket thing, which is an optimization using, that's going to be a minimization. The knapsack is a maximization using DP. The lunch ticket is a minimization, and then we just talked about some enumerations. So there's a lot of things going on in DP, and you should see as many of those as you can. If you can see 5 or 10, there's really, I would think of a class of like 6 or 7 major DP solutions, and then the rest of them are just different versions or a mapping of one solution to a different problem. So if you can see a few more DP solutions before you have to write one from scratch on your own, you will be much better served. All right, it's my favorite time of day, lunch.